All right, let's talk about something we all know way too well, buggy software. It seems like it's just a part of life, right? But what if it didn't have to be? Today, we're diving into a really powerful idea from a computing pioneer named C.A.R. Hoare. He asked a crazy question. What if we could build software that we could prove mathematically was perfect? Let's get into it.
You know the drill. Your app crashes for no reason, some weird glitch pops up, or you hear about yet another security flaw. It just feels inevitable. We restart our devices, we install the updates, and we just cross our fingers. But really, this whole cycle of patching and fixing things after they're broken, it's a symptom of a much deeper problem with how we actually build software in the first place.
Okay, but now just imagine a totally different way of doing things. A world where instead of just hunting for bugs after the fact, we could actually prove with the certainty of a math equation that a program does exactly what it's supposed to do. That was the game-changing vision of C.A.R. Hoare. See, for him, programming wasn't just a craft or an art. It was a rigorous engineering discipline. This quote right here, this is the absolute core of Hoare's entire philosophy. He is basically saying, look, if we start treating programming with the same seriousness and logic as mathematics, we can reach a level of reliability that's just completely out of reach with our current test and hope for the best approach. It's a total mind shift.
So, to turn this big idea into something people could actually use, he developed what's now called Hoare Logic. Think of it like a formal system, a set of airtight rules that lets us reason about our code with mathematical precision. Instead of just running the code to see what it does, we analyze it statement by statement using pure logic. And the secret sauce to Hoare Logic is this thing called the Hoare Triple. It's a really elegant way to frame a piece of code. First, you have a precondition. This is what you state must be true before a line of code even runs. Then, after the code does its thing, you have a postcondition. This is what you guarantee will be true after. And if you can prove that the precondition and the code logically lead to that postcondition, bam, your code is verifiably correct for that one job. Now, you might be thinking, okay, cool academic idea from decades ago. But Hoare's ideas didn't just fade away. They planted a seed that has grown into a huge modern effort called the Verified Software Initiative, or VSI. And their mission is to bring this level of mathematical rigor to the entire software industry.
The VSI's goal is nothing less than a complete transformation of programming. It's about moving from that left column, where programming is often this error-prone craft of trial and error, over to the right column, where it becomes a true engineering profession. The key phrase here is correctness by construction. You're not fixing bugs later, you're building software that is provably correct from the ground up.
So, how are they going to pull this off? Well, their strategy really stands on 3 pillars. First, you have to keep refining the foundational theory. Next, you got to build practical tools that real developers can actually use day to day. And finally, and this is so important, you have to run real-world experiments to prove these methods actually work in the wild, not just in a lab. Speaking of experiments, let's look at an amazing one that put all of this to the test in a huge way, the Tokaneer project. This was a serious industrial-scale project designed to see if this whole vision could actually hold up under real-world pressure. And the mission they were given was intense. They had to build a digital gatekeeper system. So think about a super high-security access system, maybe for a government facility or a power plant, the kind of place where a software failure is just not an option. It had to be verifiably 100% secure and reliable, no excuses. To do this, they used a very specific 2-step process. First, instead of just writing down the requirements in plain English, which can be super ambiguous, they use something called Z notation. It's a way to create a complete, mathematically precise blueprint of how the system should behave. Only after that blueprint was proven correct did they actually start writing code, using a language called Spark, which is specially designed with these formal contracts built right in. So, the big question, what happened? Well, the result was a massive success. The Tokaneer system was formally proven to meet its incredibly demanding specification. This wasn't just about finding fewer bugs. It was about proving the complete absence of whole categories of errors. It showed a level of reliability that's just on another planet compared to what normal testing can do. The experiment worked. Which, of course, brings us to the big flashing paradox at the center of all this.
We have this powerful, proven method for building ultra-reliable software for the stuff that really matters. Power grids, medical equipment, airplanes, you name it. So why isn't everyone doing this?
And the answer, believe it or not, is more about culture and people than it is about technology. There are a few factors for sure, but the source material points to one deep, underlying barrier, a widespread fear of mathematics in the industry. These methods are often seen as too academic, too complicated, or just too different for teams on a tight deadline.
So here's the most important takeaway. The problem isn't that we don't know how to build better, safer software. We absolutely do. Hoare's legacy and projects like Tokaneer prove that the theory works and the tools are there. The real challenge is about adoption, about changing mindsets, and maybe about getting over that fear. And that leaves us with one final, pretty heavy question to think about. As software runs literally everything in our world, our cars, our hospitals, our banks, our entire infrastructure, is a fear of math really a good enough reason to not use the best tools we have to make sure it's all safe?